Hello everyone, welcome to the next session on ANSYS Workbench tutorials. In this session, we will analyze the water bottle for explicit dynamic analysis. We will start by double clicking on explicit dynamics. We'll first go to engineering data and double click. We'll go to engineering data sources. Here we'll go to explicit materials. Three material. We will start with the first one, which is aluminium. Now, water bottles can be made of aluminium, copper, and stainless steel. It can be made of plastic also. I am analyzing for three different metals. The first one I have chosen is aluminium. Next, I will choose stainless steel. And the third one is copper. Now, if you want to see the three materials, just click on engineering data sources. You can see all the three have been selected. Now I'll go to project and I'll update the project. Next, I'll go to geometry and right click. I already have the model made with me, so I'll directly import the geometry. I'll give you the link for the geometry so that you can download and use it for the analysis. Next, I'll go to model and double click. We'll first go to geometry. Here there are two parts. The first one is the cap of the bottle and the second one is the body. Now we don't need the cap, so I'll right click here and I will suppress the body. For the second one, I'll choose the first material as say copper. Next I'll go to mesh and I'm going to update the mesh, or I'm going to just generate the default size of the mesh. If you want, you can make the mesh more finer. I'm going for the default size because I'm using the student version. If I use a more finer mesh, I will land up into an error. But if you are using a paid version, you can go for more finer meshes. Once the meshing is done, we'll go to explicit dynamics. Here I will click on analysis settings. I will choose the end time as 0.001 second. Then I'll right click on explicit dynamics and I'm going to insert fixed support at the bottom of the bottle, because when you place it on the table it is going to be fixed. So I am going to select these edges and click on apply. Now we are analyzing this bottle for a crushing analysis. So it is a time-based analysis that we are doing. I will right click here and insert pressure on this circumference. Generally, when you want to crush the bottle, you press it over here at the center. So this is my geometry. Now magnitude is going to be a little bit varying, because first I'll show you with a lower value of pressure. Say I'm going to give the value as 5 megapascal. This is a lower value of pressure that I'm assuming. Then we will increase the pressure and we will see the difference between application of 5 megapascal and a little higher value. So we'll go to solution now, right click, insert deformation total. I'll right click, insert deformation directional. I want to see the deformation along the x-axis. Also, I want to see the directional deformation along the y-axis. That is the vertical one. Then I'll right click and insert strain equivalent and the stress equivalent. Then I'll go to solution and solve. Now explicit dynamics as compared to other solution take longer duration of time, so you will have to wait for it. Once you've got the result, you go to total deformation. You can see here the maximum deformation is 14.966 mm. You can see the body has also deformed. Here you can see these are the values of maximum, minimum and average deformation. Minimum is 0. So here you can get the value of maximum and average deformation based on time. So when I animate, you can see the result in the form of animation on this water bottle which is made of copper. Next we'll go to directional deformation. This is along the x-axis. Here again you can see the graph of the deformation versus time. Here there are three values as shown in the table form also. It is minimum, maximum and average. So suppose if you want to see the maximum value, you just have to remove the stick over here. So now you can get the value of maximum value. Even if you don't want to see the average, this is the graph of deformation which you can see. You can animate and check this result as well. You can see where the value is max and where it is minimum. Maximum is 8.65 mm, minimum is minus 9.028 mm. So these are the values. If you want to see the max min, you can click over here. This is the maximum and the minimum value. Now if you don't want to see this mesh, you can go to edges and select on no wireframe. You can see here these are some bands which are formed. So you can go to contour and select smooth contour such that the colors blend into each other. Or if you want to see the bands, it is fine. If you want to keep the mesh, just go to show elements again. If you don't want to see this max min, click on them once again. So these options will disappear. Next we'll go to directional deformation 2, which is along the y-axis. So you can see the max value is in red color, 7.324 mm. Minimum is minus 0.808 mm. Here again the table form is showing max, min and average. Whatever value you want to see the graph, you can keep it that way. Then you have the equivalent elastic strain over here. You can see the maximum strain is 0.0035 and minimum is 5.3681 into 10 raised to minus 5. Want to see where it is max and min? Click on max min. And the last one is equivalent stress. The maximum value is 372.98 megapascal and minimum is 2.1061 megapascal. You can again animate and check this result. If you want to see the stress versus strain graph over here, you have to insert the chart option which you can see here. So click on chart. When it is asking for object selection, click on stress and strain both and apply. X-axis is going to be the strain. So we want to see the equivalent strain maximum. Next on the x-axis label, I'll write here this is the strain. Y-axis is the stress. Time I don't want to see, so I'll omit. Then here display minimum I will omit because I don't want to see, and minimum stress also I don't want to see. So you can see here this is the graph of stress versus strain for this body given this value of pressure. Now I had told you at the start of solution that we are going to analyze for two different values. This is one deformation that we have seen. Now suppose if this pressure is increased, crushing pressure, and if I give 10 megapascal, so I'll just solve once again and see what kind of results I'm going to get with 10 megapascal. This will again take a lot of time, so you need to be patient and you have to leave the analysis for solving it. So now you can see the solution has been generated. We will see the total deformation. So now you can see the condition of this bottle. It has got completely crushed. I'll just select this max min once again so that it disappeared. Because now I think you can click on max min and you can see the result. What was important for me was to show you that when the value of pressure for crushing was 5 megapascal, you got a different sort of deformation. The value was also very less. Here you can see the deformation is 51.57, which is approximately 5 centimeter, because of which you can see such a large crushing effect. Now this will be seen in explicit dynamics and not in a normal static structural analysis. Because this is a time-based analysis. Over a period of time, this kind of deformation is going to take place. So this is one. Then you have directional deformation. This also you can see the highest value is 36.035 mm along the x-axis. Along the y-axis it is less, it is 20.761 mm. Strain value maximum is 0.0035 and stress you can see is now 398.11 megapascal maximum. The minimum value is roughly the same as that of 5 megapascal, but this has increased. If you want, you can see the chart, you can see the values now, how it has changed. So we have analyzed for copper. Now I'll show you for one steel. So we will go for changing of material. You click on this geometry. Here we will change this to stainless steel. I'll go to solution and solve once again. So we have got the result. Let's see the total deformation. You can see it is just 0.38 mm and the pressure that has been applied is 10 megapascal. I have not changed the pressure. So this is the amount of deformation which is very less, which means that copper bottle will get affected more as compared to steel. You can animate and check this result. So the maximum deformation is 0.499 mm. Then we'll go for directional deformation. Here you can see it is 0.308 along the x-axis maximum. When we go for the y-axis, the maximum is 0.3454 mm. The strain value is 0.0035166 maximum in this zone. And the stress again in the central portion is 659.52 megapascal. So you can still see that your body is safe because you have very less amount of deformation over the body. You can also see the chart here. It is still representing the maximum stress and strain over this body. Now here you can see that the deformation is quite less, which is 0.38748 mm. So when you get this value, you are sure that your bottle is going to be safe under this pressure. Now you saw for copper, the crushing was completely happening. For steel, it is not happening. If you want, you can check for aluminium. You have to just change over here to aluminium and you just have to run the solution once again. So let's see the result. You can see here the solution has been obtained. This is the first result of total deformation. You can see that deformation is highest in case of aluminium. It is 71.497 mm because aluminium is the softest material. So obviously when you apply load which is of crushing type, the maximum effect will be seen on aluminium. So if you think about some kind of soda cans which are made of aluminium, this kind of crushing happens in that. Next comes directional deformation along x-axis. Highest is 44.6 mm and lowest is minus 51.372, which you can see by color. Then is directional deformation along the y-axis. Maximum value is 55.068 mm. Strain is 0.004. Maximum, minimum is 0.00023 and stress is 288.27 megapascal. So you can see that when you do a comparative analysis of three materials, steel being the strongest or the toughest, it is not going to crush at all. It is going to show very minor deformation. Then comes copper, which will try to resist the maximum, but still it will show quite an amount of crushing, which is 5 centimeter if you recollect. And aluminium is showing the maximum deformation or the crushing effect, which is of 7.1 centimeter or in terms of mm. If you want to see in centimeter, you can just change here. So you can see it is 7.14 centimeter. So this helps you analyze a bottle by using explicit dynamics. For a given range of time, we have taken the end time as 0.001 second. You can change it and you will get some different result obviously because you have given either more amount of time or lesser time. So accordingly your bottle will show the crushing effect to a certain extent. With this I end the session. I hope you have understood the analysis. If you have any doubt, please write to me in the comment section. Don't forget to like, share, and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.